ಆನ್ ಮಾಡಿದ್ರೆ ಅದು ಕ್ಯಾಮ್ರಾ.
ಇದು ಲೈವ್ ಲೈವ್ ಬರ್ತಾ ಇದೆ, ಒಂದ್ಸತಿ ಚೆಕ್ ಮಾಡಿ ಯಾರಾದ್ರೂ, ಆಯ್ತಾ? ಸೊ ವಾಯ್ಸ್ ಆಡಿಬಲ್ ಇದೆಯಾ? ಇಲ್ವಾ? ಅಲ್ಲ, ಇರೋ ಯೂಟ್ಯೂಬಲ್ಲಿ ಬರ್ತಲ್ಲ ವಾಯ್ಸ್.
ಇದು ಹೊಸ ಲಿಂಕ್ ಶೇರ್ ಮಾಡ್ತಿದ್ದೆ, ಝೆಡ್ ಸ್ಕೋರ್ ಇದೆ. ಒಂದು ಸೆಕೆಂಡ್
ಇನ್ನೊಂದ್ಸತಿ. ಓಕೆ,
ನಾನು ಲೇಟೆಸ್ಟ್ ಒನ್
ಇಲ್ಲ ಇದು
P2000. ಓಕೆ, ಲೈವ್ ಒಂದು ಸೆಕೆಂಡ್. ಸಿಕ್ಕಿತ್ತು. Yes, it's working.
ವಾಯ್ಸ್ ಆಡಿಬಲ್ ಇದೆ?
Yes.
Okay.
Yes, it's working. Voice audible ಇದೆ.
ಸರಿ. Okay. So today I think we'll go more with the theoretical exercise. Last week we have discussed on Z-score, what exactly Z-score is and how is it useful in detecting the outliers. So it's a part of feature engineering in machine learning. So when we start with machine learning, we have something called as feature engineering, where we try to do some pre-processing tasks in selecting the features and detecting certain unusual or non-usable data, or some of the transformable data. We try to identify that using feature engineering, or we can create even new features using that. So it's a part of the machine learning subject. So there we can use Z-score as a technique to identify that particular feature, the outlier in a feature. Okay, so last week we discussed about what is Z-score and what are the different tests which needs to be done to identify the Z-score method, and some of the use cases of that, right? So today we'll just start with more of how to do that theoretically. So we'll try to do even the exercise. So when we say Z-score, we calculated last week what is Z-score, and I said that there is something called as table. Okay, so the table denotes the probability of that, how much probability of the data might be occurring, which will help us to interpret the Z-score value. So as I have written the definition here, so the proportion of data points that fall below a certain Z-score value in a standard normal distribution. So last class we had discussed what exactly is standard normal distribution. Okay, so what exactly Z-score does. So when we have any data which is distributed, maybe any kind of distribution, we calculate the standard deviation, then the mean value, and then calculate Z-score to normalize it to such a way that the standard deviation the mean value will be 0 and standard deviation will be equivalent to 1. So same thing we had discussed right last week, where you have some data here, you identify the mean, and here the mean value is not 0. Okay, so you even though it is normally distributed, the mean value is not 0. Just to scale it so that it is easy to interpret in when you try to feature scale or do feature engineering, we try to standardize or scale it into a common neutral format, which is nothing but Z-score. So this is what we did, from normal distribution to standardized way, where it will be 1 sigma, 2 sigma, and 3 sigma, where sigma is nothing but the standard deviation. So from mean value, how much does particular data point vary? So once we calculated the Z-score, now to understand what does this mean, okay, from the values we were able to understand in this use case that whether it is a failure or what exactly is that, right, with the help of the inference. But when we use the table, we'll be still more able to understand what is it how is the data distributed with the help of Z-score. So that is what this definition means. So now today we'll take a use case of anomaly detection. Okay, so when we say anomaly detection, how could Z-score help in that? Suppose if you have a data point and the Z-score is very high, whether it may be in positive sense or even in negative. Okay, whether it may be in this positive region or even in negative region, if it is very high, it means it is very far from the mean value. Okay, and it means that the likeliness to occur and under the normal circumstances, it is very less. Suppose if we assume this is a normal circumstances, okay, this range, then if some z-score value occurs very high with a very high value, then the likeliness for it to occur within this range of like say maybe safety region, or what I can say is the normal operating range, is very less. So then we can term that as unusual behavior based on the threshold value what we give based on the domain knowledge again. So when we discussed last week example, we could see that most of these values were within 1 sigma value. We know that z-score represents the sigma value, right? Here it will be 1 sigma when the z-score is equal to -1. But, or sorry, this is, yeah, minus sigma, and this is plus sigma. And when we see here, it's more of 0.3, 0.23. So it means that it will fall somewhere here between 0 to 1. So it means it is within 1 sigma. So there is a probability that almost like say when we have this, we can say around 66% of the data is distributed over here, and most of the data might be occurring within this mean range itself. But we could find the anomaly, like say, I think we should have, yeah, 2.42. So when we say 2 is the threshold value, then 2.42 z-score, it means it is more of that unusual behavior which is getting represented, right? So that is what we have understood up to last class here when we calculated it. So that is what even this particular like say sentence is trying to communicate. Now, in this case, let us say the 2 sigma is the limit. Okay. So what does that mean exactly? So that nothing but means 95% of the data will be falling within that particular standard deviation from the mean. Same thing. Suppose if I say it is 3 sigma is my threshold. At that point of time, it means almost 99.7%. So generally this center, like say line, it represents the, it's a mirror image, right? See, if I take this as a total data set, 50% of the data lies on left side and 50% data lies on the right side. It is more of a bell curve, which represents the entire data distribution. So when I say 99.7%, it means this, it comes under this dark green, light green, and yellow region. Same thing on mirror image. So total almost 99.7% represents that. The remaining data is represented as an outlier when we say z is equal to -3 or +3. Same thing when I said 95%, it means 95% of data was contained in light green and yellow and light green, this region. Okay. That is why we try to normalize with this scalable values 0, 1 sigma, 2 sigma, 3 sigma. Because if in earlier case when we have when we were trying to do that here, it is very difficult to identify that. Even though we get mean value and standard deviation, it is not standardized, right? So that's why we try to standardize it with the help of z-score, so that outlier removal or even feature engineering is very much easier. So next we'll just have an use case. So we'll try to do this manually. So if you are having access to laptop, you can just open the Excel sheet. So I'll try to share this data. Okay. I think so that you can calculate z-score manually. So 1 minute. Okay, this sharing is image. Okay, I'll just share it as text then. So you can take this data and open Excel sheet. Okay. So once you have that Excel sheet, you can just format it in this form, this way. Like it's the reading, or it can be even time, right? Here I have taken a scenario where we have a centrifugal pump. Okay. So we have a centrifugal pump, and there is some vibration for that. So it will be something maybe vibration. Okay, so it might represent something like this. some data like this. Okay. So this is the vibration measurement of that, which is there in the unit of millimeter per second. Maybe it's a velocity. So once you have that, so what is the first step to calculate the Z score? So we know from the formula that Z score has x minus mu divided by sigma, where mu is nothing but the mean value and sigma is the standard deviation. So we have the x point, right? Already we have the data, the data which I have shared here. So we have x value, that is the vibration displacement or velocity or acceleration. It can be anything. Okay. So this can be taken as time data. So when we have that, first we'll calculate mean value. So you can calculate mean value and let me know what is the mean value of that. So how many of you have like Excel sheet, access to Excel sheet?
I'm trying to open it now.
Okay. Yeah.
Sometime.
So you know what is the formula to calculate mean, right? So I think it is there in, it was there in initial classes.
Sum of all the
sum of all. Yeah, I think it should be somewhere here.
Where
Yeah. So sum of all values divided by the total data count or the data points. In Excel sheet, you can use this particular formula. Sorry, sum. You can use the sum and yeah, you can take it. And then you can just use count. So that will calculate the total number of data points. So this sum divided by that count will give you the mean value here. So this can be done even through Python. So this I thought first we'll go through Excel sheet so that you'll be able to understand it. Then that will be useful in programming, in developing the program. Because once you are able to do that in Excel sheet, then you know what is the logic needs to be followed. So then once you know how to do the programming, you can follow the same logic for that. So everyone is done with this up to mean value.
Yeah.
So yeah. So once we are done with the mean value, then we need to calculate the variance of that. Okay. So it means how much is it varying from the mean value? That is from this center value, right? Or the not center exactly, but the mean value of that. How much is it? Each individual data point is varying. So that is what it represents here. So you can just subtract it. So once you subtract that from the mean value here, you'll be getting that value here.
can just drag down.
Yeah, you can just drag it down. So you once you square it, you get that variance. Yeah. Then you need to calculate the standard deviation. So that's nothing but the square root of that variance value. So I think we discussed this in previous class, right? So it brings back the unit. Original unit of the vibration was in millimeter per second. So when you square it, the unit goes off. I mean, it is not a realistic unit. So it brings back the unit. So in this data, we know 589 or roughly 0.59 millimeter per second is the mean value. So it will be somewhere here as a, I think somewhere here, I have shown it here. So this will be somewhat millimeter. Yeah. Mean value will be somewhere here, I guess. 3.4. Okay. Yeah. Mean value is 3.4 here. That's what I have shown here. You can see it here, right? So this is the data distribution, a histogram plot. Okay. So it means most of the data were here. Only certain data is here. So you can see even in graph, it's outlier, right?
Outlier.
Yeah. But we don't know, like we'll have to assess it. Yeah. Just with the distribution, sometimes it might be useful data. So we can't just eliminate it. So this red line represents the mean value. So this is the distribution. Okay, normal distribution. That's what we see here.
Mm.
So once you calculate, you identify the standard deviation. Okay. So everyone is done up to here, right? Standard deviation.
Mm.
Anyone? Any confusion?
Can you share the data once again, Nabi?
Yeah, it's there in the
Join
text.
that.
Okay.
Laptop.
Meanwhile, others can just use this formula. Okay, so you have calculated x minus u here, right? So you can use that and then divide it by standard deviation, which has been calculated from here. So you're getting same values, right, for this?
Mm.
So if everyone is getting same values and done with this, then we'll go to the next step. Is it okay if everyone is done? Because that requires for you to open a table. Yeah, this one. You can type Z score. Okay.
Why did you
Yeah.
square x minus u?
This I squared because we want to calculate the standard deviation. Okay. So if we go here, I have the formula. I think 1 minute. So we calculated in earlier classes, right? Variance formula: x minus mu the whole square divided by n minus 1. Okay. So to calculate standard deviation, we need to take the square root of that variance. Okay. So basically, what it represents is the deviation of that point. Suppose if the data point is somewhere here, somewhere here, how much is it varying from the mean, or where exactly it is lying?
Numerically.
Yeah, numerically, kind of distance formula. Because even in distance formula, we have that, right? Root of x2 minus x1 the whole square plus y2 minus y1 the whole square between 2 points.
Yeah.
So once that is done, is it like even this is done? This is calculated.
And you continue, Abhi. I'm doing it.
Okay. Because next step is important step, because till here at least I think we had even done the exercises last time. This can be checked here also with the previous examples. Okay. Same thing can be even you can go to the previous video and take this particular data and calculate Z score for that. Yeah. Next part is crucial. That's why.
Then I'll do another.
Yeah.
2-3 minutes.
So meanwhile, others you people can just open this Z score table in Google Images. Okay. So as discussed, see this but next table, this is nothing but it is called a Z score table. It represents the probability of that particular data point to occur. Earlier we identified with how much standard deviation it is there. Now it says with that particular standard deviation, what is the probability of that to be there with the cumulative distributed frequency. So with the help of the centrifugal example, I'll just detail it more. So if this is done. So till now we have completed mean calculation, standard deviation, and z score for each data point. Okay, so we can make it as green. So is this done now? Sorry, I mean this z score is done, right? This calculation. So if you open this table, you will get something like this. Okay. So now in this first value, if you see, it is minus 0.3475, right? Now open that table. So it is minus 0.34. It means it is lying on left side of the curve, right? Okay, so it is minus 0.34 here. And it is 34757. So I can take 347 somewhere here, right? Minus 0.34. Sorry, this is minus 3. Minus 0.34 I need to take. Minus 0.34.
Below.
4 is somewhere here. Yeah, here. So it is 0.36693. Okay, so you can take that value and put it over here. So this is the value from the table. So this is the probability. Okay. Hope this is like clear, right? You understood from how to take that.
So this table is every time we have to use it, right? So
no, now in Python and all it will do it automatically. You can do it. This is just I'm teaching you. I mean manually. That's why I took Excel sheet. In Python and all, we have direct libraries for that. You can calculate. No need to go in depth as much as this. But why I'm going through this in depth is because we'll be able to give the inference very much easily when we get the values. Because if we're able to understand this theoretically, right, how it is occurring. Like we understood what is standard deviation, what that means, like how the point is varying from the mean. Suppose, let us say, if a particle is vibrating or a component is vibrating with maybe around 3.5 or 3.2 in this case, right? Suppose if the mean value is roughly around 3.45, so it means that it is somewhere near the mean value it is vibrating. Right? If you check the curve, let us let us take this example. Like say, if the mean value is somewhere here, 3.2 may be somewhere here, the amplitude. We are not sure. It might be for different excitation ranges, the displacements. Like at certain RPM, 3.2 might be somewhere here. 3.4 mean is somewhere here, right? It is somewhere here, 3.4. 3.2 is less than the mean. It might be somewhere here when it is operating. But whether it is anomaly or not, we don't know. But it is also possible that this particular pump might be vibrating in this from starting from this range up to this range. So it will vary only from here. Mean value will be somewhere here. I think I'll just check if it is possible to. Let us take this as a range. Okay. This is one. This is min range. And somewhere this might be the mean amplitude, the blue one. So if in this case, the blue one 3.4 is blue, this might be 3.2 and this might be some very high amplitude, maybe 3.5 or 3.6. Okay. Let us say it is operating too much in this. So it means more data is distributed here. Like this here in this case, it is most of the data is within this only, right? 3 to 3.5. So it might be this date only. Maybe in certain cases, the data might be going here. Like suppose if we travel by a vehicle from home to office, if I'm going in a constant speed, maybe in 3.2 millimeter per second, that speed, assuming hypothetically, okay. So it means most of the time I'll be going in that speed only. Then when highway we might hit, we might go with the higher speed. That's with this speed.
Right.
But when we take the average, then we can say it is 3.4. So it means most of the data will be with the 3.2 bin somewhere here, 3.2, 3.3, the most of the data will be there. High wave might be this one, where we go very high. So it means it will operate there only. And when we put this data distribution for this particular data, then it will be something like this. So this will be 3.4 and 3.2 might be somewhere here. Okay, and 3.5 might be somewhere here. But it is the data is falling under this most of the data area, maybe around 66%.
So it is up to us to determine whether it's we have to take 66% or whichever it is.
It purely depends on domain knowledge.
Domain knowledge, correct.
But most of the time we assume that see the data will be distributed here and outlier.
Right.
Yeah, we can decide whether we want it or not. Because there are even other different techniques for the outlier treatment. We have something called as trimming and capping, where like suppose in case of capping, what we do is, suppose if you have outlier here, okay, I think somewhere it should be there. Okay, I'll not put the box plot. Suppose, yeah, in this case, suppose if I have -3 as outlier, in capping method, what I do is I take this is the maximum value -1. I convert this -3 into -1 only. Or here in this case, if I say 8 is the maximum value as outlier, 11 is the outlier here,
right.
I convert 11 into 8 only, so that data point doesn't get disturbed.
Right,
Trimming
right.
is,
I can extend this
yeah,
limit, yeah.
trimming is I remove the data point of 11 itself. I don't cap it.
Got it.
So they are feature engineering
we can
technique.
chop it off, or we can chop it off, or we can extend this bell curve.
Yeah, kind of converting the value into maximum outlier value.
Value into maximum.
Yeah.
Right.
So they are feature engineering techniques. That purely depends on your, like say, machine learning problem. So we'll have to test in both the ways how your like model is performing or not. Okay. So once that is done, now you know this, right? So we can even take other next value, 0.16, right? 0.16107. So if I go to the table again, yeah, I'll go to the table again.
0.1 and 6. Below.
Yeah, 0.1 and 6.
0.1.
5636. Okay, 56356. So that is somewhere here. So when we say this, right, it actually represents the area to the left of that particular curve. Okay. As I said, the entire bell curve represents 100% data. Now I'm having this data here. Okay. It means this left side of the curve is represented by that area of that, the probability of occurrence. So next value, suppose if you go with the this last value, 4.06. Okay. So 4, if you say it is not available here, okay, but 3.9, if I say it is almost 0.9997, right? I can take it as 0.9999.
Correct.
Okay. So now already we know Z score value in as per this threshold. I assume that Z score with anything value greater than 2, okay, we'll consider that as anomaly. It means something which is greater than 2 here, we'll consider that as anomaly. We can even consider 3, but in this current scenario, I'm saying anything above 2, that is anomaly. So in score itself, we know that is anomaly here because the value is 4. It is very high compared to 2, right? All other values are very less. But now with 0.999, I know it's something like there is a 99.99% that the rest of the, the 99% of the data is present on the left side of the curve. That is here. That is what it says when it says 99%. It means 99% of the data is on left side of the curve. Only that 0.01% is on right side of the curve. That is what this Z score, I mean, this particular Z score table mean. The value what we get here, right? That is what it refers to. This 0.997, it represents, it says that when I calculate here, if my Z score value is somewhere here 4, 4.0 something 06, it means when I check in the table, it says 99.99%, right? So it means that 99.99% data is somewhere here. Only that 0.01% data is here. That is what it says that.
Yeah, but imagine like we have one value of 4, we have multiple values, maybe 3 and 2, and
Then
then
for each and everything, it will
normal
give a
construction.
different value. Like say in
Yeah.
this case, I have said right. Okay.
Mm.
See here, z is equal to
Suppose
0 represents the mean value.
mm-hmm.
Next, I say z
Correct.
is equal to minus 0.35. I think that is
Mm.
what is here, minus 0.35. This one only.
Correct.
Okay. So what it represents in this curve? Okay, it is somewhere here. It represents, yeah, it represents 3.2 like millimeter per second, that particular vibration data. Okay. So it means, as I said, this vibration data, 3.2 millimeters per second, it is very much near to the mean, which is 3.45, right?
Mm.
And when I get this as a from Z-score table, if I get this as a 0.36693, which is 36%, so it means that the remaining 36% of the data is there on the left side of the curve. That is this part.
Mm.
So it means that much of data is there on that side, which means the remaining part is on right side of the curve.
Correct.
So now we say 4.06. Same thing. It is 5.8 millimeter per second. That is very high value. Okay.
Mm.
So you can see it's somewhere here. The purple line, above the purple line. Sorry, on the right side of the purple line, right? 4.06. So it means that almost 100% of percentage of the data is lying on its either side,
Left. Left
right?
hand side. Left.
So that is what it represents when we say 0.9999. Because just with sigma value, since we have said, okay, we can say that, right? But what is the probability or amount of data which is present? That is what Z-score table says. The proportion of data points that fall below a certain z-score value. Okay, so that is what the table signifies there. How much amount or percentage, in terms of percentage, how many data are there? I can say 90% of data or 100% of data is there. When I say just with z-score point, like say if z-score is -1, I can just say -1 sigma, but I don't know how much percentage or yeah, how much percentage of data is there within that region. That
On
is
the
where
left hand
z-score
side,
table
yeah.
will help us to infer that.
Mm.
Okay, I think, yeah, that's what I've written here. If 99% of the data is to the left of 4.06, remaining percentage is 1 minus 0.999, which we got from the z-score table, which means it is
Correct.
0.000, which is 0.01%. So it means the occurrence of that, it is just 0.01%, the probability,
Mm.
which is a like very high value. And then
Mm.
we can consider
So
that as
this
an
is
anomaly directly.
yeah. So this is now what we are doing is like using this data, we are predicting that what are the chances of data coming within that line or which is beyond that line.
No,
So that is what we are concluding here.
let me say in other
Or
way. Okay,
in a
like
way.
say
Mhm.
I have z is equal to 2 sigma. Okay, I say
Mhm.
that is anomaly.
Yes.
But what is the
Mm.
percentage amount of data within that anomaly, like non-anomaly region, and with this within 2 sigma
Right.
to 4 sigma? Suppose if we say there is more
66%.
data within 2 sigma to 4 sigma,
Mhm.
then I can't say that the percentage of anomaly is like I can consider it significantly as anomaly, right?
Right.
So to take up that call, then we'll have to analyze in this way.
Mm.
Suppose if it is very less data, percentage of data is very less here, then we can say, okay, we might consider that as anomaly. But if there is significant data
Mhm.
even within 2 sigma to 3 sigma range, then we need to
Mm.
rethink about it. That's where this Z-score table
Correct.
will help us to understand that.
Yeah. So now we have to analyze in that case each and every data where how much percentage of data, which region it is concentrated,
Yeah,
and
yeah,
then we can come up with a decision like whether that can be taken as anomaly or like whether we need to take it
yeah. So all
as
these
a
things are done
most
automatically in Python with the help of libraries,
right.
but this is just
Okay.
a
Right.
background of that.
Yeah. Example. Yeah.
Yeah, example. Because like what does that mean physically?
Mm-hmm.
So in this, I've just written the inference. So we can say most of our vibration readings have z-score between -1 to +1. That's what we have seen here,
Mm-hmm.
right? It is only
Mm-hmm.
with certain one value that it is very high. That is 4.06.
Mm-hmm.
Okay, so it means 95% are within that particular good range. Okay. So for centrifugal pump, then I think we'll have to like understand what does that mean. Okay. So here I have written that okay, we need to check the pump whether there is a loosening of the part, bearing where is there, cavitation is there, or misalignment. So all these things needs to be done in physical sense when you have such kind of anomaly. So I think this is very much useful for Anvit's case in digital twin. If you're doing a PSD vibration, this is very much useful. Because even in PSD, you take output as probability, right? 1 sigma, 2 sigma, 3 sigma. So there you can
Video
take
is not
it.
visible in YouTube results.
Huh?
Video is not someone has messaged.
Video is not visible. Huh?
Now it's messaged. At that time it was visible.
In YouTube, which one? Yeah, like YouTube or?
Wait, let me check. Yeah, I think video is not.
It's not visible.
Only voice was there.
Oh. Okay. Anyways, I'll retake it then if that is the case. Nah, not an issue. Because this is a very small concept.
Correct. Yeah. Okay, just go through it the next class just quickly and then.
So yeah, we got two values, right? I think this still more in detail I have put it. So first value we had got 0.16 here, and the probability of that is 56.356, right? So what does that mean? When we say 0.16, it was for vibration level 3.5 millimeter per second. So it means the 56.35%, if your pump's vibration levels are normally distributed here, so 56% of the data, so 3.5 means somewhere it will be on this side, somewhere here, I guess. Somewhere here it should be, because this is the mean, right? So it means 56% of the data is lying on left side of that. So, and that data is lying there, that particular point is lying over there. Okay, that is what it means.
And what should be the value if it has to lie on the extreme left, Abhi?
Extreme left. This is purely based on our initial calculation. That is the standard deviation.
-4 if it's
Yeah, -4, -3. Most of the time, like if it's normally distributed, we give 3 as the limit. 3 to +3 to -3, and we whatever falls outside that we give it as a anomaly condition. Outlier. Yeah. In the certain cases, we can even take 2 + 2 to -2, because we assume that almost like in this we have shown, right, almost how much, 34 plus 13.5 plus 2.3, almost significant data. This is around 30 60. Okay, 68% data lies here. Then you add some like 13%, that is 13 rings to 26. Okay, so up to 2 we can consider very good data. Then what are after that? This is purely dependent on domain knowledge. We'll have to understand that and then check it. As I said here, suppose if we say this is around that roughly around like 66% comes here, okay, and remaining percentage comes here up to 2 sigma. Then if we have some data, if this is like very much useful data, we can use the capping method or trimming method. So in trimming method, we take 2 sigma or 3 sigma itself as a final value, and we remove these data points from the data in machine learning. Okay, I think this is still more we can representative. So 1 sigma is up to here, 2 sigma is 2 times the standard deviation, 3 sigma is 3 times the standard deviation limit. So in capping, we can take, in this case, if it is a stress value, we can take whatever comes above 153, we can convert everything into 153 limit. Whatever comes up to above 194, we can take everything into 194 as a limit, if it is the capping method. If it is trimming, we can directly trim in 194 and 153. Whatever data points comes on either sides, we can just directly remove that in the machine learning data pre-processing. So that will have to actually check and remove how your model is performing based on accuracy. or whether it is significantly important. Like suppose if we take a FEA problem, some in like stress analysis, most of our data will fall here only. Only the failure locations will follow as outlier. Then it means we can't trim it out, right? Hello, is it audible?
Yeah, audible.
Yeah, yeah. Okay. So we can't remove that stress failure location as a outlier, right? Then we'll have to go